Hey everyone, welcome back to our playlist on object-oriented programming. In this video, we'll be learning about compile time polymorphism. First, we will go through some concepts and then we'll look into the code. The topics covered will be what is polymorphism and its types, what is compile time polymorphism, function overloading, and operator overloading. The word polymorphism is derived from poly, meaning many, and morph, meaning forms. So it is the characteristic of being able to assign a different meaning or usage to something in different contexts. Specifically in object-oriented programming, it means to allow an entity, such as an operator or a function, to have more than one form. Let's have a look at this code snippet. We have two functions, both named printMe. However, their definitions are different, meaning both will perform different tasks. Polymorphism allows us to define such functions and use them without any ambiguity. When there are two or more functions with the same name, let's say printMe in this case, a decision has to be made regarding which set of instructions has to be executed when the function is called. Let's go ahead with the two types of polymorphism. These are compile time polymorphism and runtime polymorphism. In compile time polymorphism, the function call is resolved by the compiler, whereas in runtime polymorphism, which function is to be invoked is established during the runtime. We'll be focusing on compile time polymorphism, which can be achieved through function overloading and operator overloading. Defining multiple methods with the same name but with difference in either the number of arguments or the data type of arguments or ordering of the arguments, and resolving these method calls at compilation itself is called function overloading. The compiler uses function signature to perform overload resolution. Hence, two overloaded functions should not have the same signature. A function signature includes the function's name and the number, order, and type of its formal arguments. One important thing to note here is that return value is not a part of the function signature. Let's see what are the valid cases of function overloading through these function declarations. In the first case, we have overloaded the sum function with different parameter types. In the second case, the number of parameters is different. And in the last case, the order of parameters is different. All of these are valid ways to overload a function. Now, there might arise a question as to why is function overloading even required? Like, why can't we just use functions with different names? So let's take an example. Think about a function you want to write that returns the absolute value of a number. The number could be anything, an integer, a float, or a double, which means you will have to define the absolute function thrice for each data type. You can achieve this in two ways, as shown here. The first way is to name the absolute function differently every time, while the second way is using function overloading. In this case, function overloading can be a very convenient and intuitive feature. The primary benefit is the consistency in the naming of functions, which logically perform very similar tasks and differ only slightly in accepting different parameters. Another important application is that of overloading the class constructor. The user may not want to initialize all member values at the time of object creation, and hence multiple constructors may have to be defined. Now let's code and apply what we have learned thus far. Let's say we want to create a class log details which keeps a track of any changes that take place in a system. It will have two data members. The first is of the type boolean called status. True will represent that the system is working fine and false will represent that there is some issue. The other data member over here, it will give a little more details about the status. For example, if there's an issue, it can say what kind of issue it is, so it will be of type string. Now let's write some functions which will be able to update or change the values of status and status detail. We pass in a boolean type of argument. And we set the value for status. Similarly for details, this time the argument type will be of string. So now we have our functions required to change the values of status and status detail. We are trying to create a logger function, which means that we want that every time the value of status changes, it is displayed on the console. So let's write a function that logs these changes. Let's call it log. Now, depending on the type of update and status, we should be able to log a different message. So we pass in a boolean value. Let's call it updated status. And we check what the value is. If it's true, we can say that everything is working fine. So we print to the console that system is working fine. Else what we can say is that there is some issue in the system. Cool. Now we have our log function ready and we'll be calling it inside change status. So every time the status is updated, the log function gets called and we have a log on our screen. So now that our class is ready, we can create an object. Okay. So let's say there's some issue initially and we change the status to 0. And we want it to be accompanied by some details. Let's say there is a problem in section B. Okay, and say after some time things turn back to normal, so we change the status again. And again we are accompanied by a change in details. Now let's try to run this program. What is expected is that every time the status changes, there is a log created on our screen. Yeah, and that's how it is working. Whenever there is a status change, we have our logs according to the condition that we have provided. However, I would like some details on my logs too. Right? Whenever there is a change in the details, I would want it to be logged, which means that I will have to call the log function inside change detail too. However, we know that we have defined log only to display the change in status. It takes in a boolean value, but now we want to pass in a string which will be displayed on the screen. Now comes the concept of function overloading. We will be redefining the function log. And this time, this is a very important thing to note, this time the argument type is different. We are calling it updated detail. Okay. And whatever this detail is, we print it to the screen. Okay. And we are calling it inside log, we are calling the log function inside change detail, and we are passing in the new status detail. let's try to run this function again, and this time we might expect that there will be some error because we have two functions of the same name. However, we can see that despite the fact that there are two functions with the same name, the code is running properly. We have all the logs placed correctly. So what is happening here? We see that even though we have two functions named the same, the function signatures are different. This is what helps the compiler to resolve the overloading. Okay, so the compiler decides which function call needs to be given when we call the log function over here. Let's try one more thing now. We'll try overloading the log function once again, but this time we'll only change the return type. So let's say the return type is string, and this time we not just print out the updated detail, but we also return a string that says change in details. Okay, so we can clearly see that the two functions are different, or so we think. Let's see what the compiler thinks, and we'll try to run this program again. Okay, we have an error over here. See the note, it says that there is a previous declaration for the log function. So earlier the compiler was able to resolve the overloading of the log function. However, now it cannot distinguish between these two functions. And the reason is that the return value is not a part of the function signature. So to sum it up, we can say a difference in the type of parameters or the number of parameters or ordering of the parameters can resolve an overload. However, the return type cannot resolve an overload. That's all about function overloading. Let's have a look at the concept of operator overloading now. What we can achieve through it is that we can redefine how an operator works. Most operators in C++, with the exception of few, can be overloaded. Again, what's the need for it? The advantage is that through operator overloading, a programmer can use operators with user-defined types as well, which means you will be able to perform operations on objects that you have created. Let's take a look at a very intuitive example to learn more about it and to understand the syntax of operator overloading. So here we have created a class to represent complex numbers. The two data members are real and imaginary, which will represent the real and imaginary parts of a complex number. Then we have defined a constructor for the class which initializes the member values, and then we have defined the print function which prints our complex number to the console. In the main function, as we can see, we have declared two numbers of the type complex. Now let's say we want to declare another complex number, and we want its value to be a summation of number 1 and number 2. This can be achieved through operator overloading. We will overload the plus operator to get the required result. Let's see how it can be done. So first we write the return type. Like in this case we are adding two complex numbers, and we would like to return another complex number, which will be the answer. So we write the return type, then we write the word operator, and we mention which operator we want to overload. In this case it will be the plus operator. After this we pass in the arguments. Now you might be wondering as to why I have passed in only one complex number, because addition will be requiring two of them. So when we will be using the overloaded plus sign, the object used to invoke the operation will be passed implicitly. So the number of arguments required will be one less. That's why over here we are passing only one complex number. Now let us declare a complex number in which we will be storing our answer. Now for the real part of the answer, we will be adding the real part of the object that is invoking the operator and the real part of the num that we have passed here. Similarly, we will be doing it for the imaginary part. Okay, and now we return the answer object. Now this should work. So in order to verify, we'll print our complex number num3. And let's try to run this. So the expected answer would be real part being 2 and the imaginary part being -4. And that's what the answer is. So we have successfully overloaded the operator plus. Similarly, we could have overloaded the subtraction operator or multiplication or division. It's very similar. The syntax will be the same. With this, we conclude our video on compile time polymorphism.